Okay, arithmetic operations in binary and hex. So we've looked at the hexadecimal counting system. We saw how computers displayed information using base 16 purely for humans to be able to make sense of very large binary numbers. Let's see now how we normally add using base 10. So I'm going to show you the equivalent in base 10 and then show you how it is performed in base 16 and then base 2. Just a recap then, in base 10 what we normally do is we place our numbers which we are going to add. So here we have 1375 adding 4614. We place them, align them together and then add them up, add these numbers up. This is a straightforward one, so 5 plus 4, we always start from the right hand side. 5 plus 4 is 9, 7 plus 1 is 8. 3 plus 6 is 9, 1 plus 4 is 5. Straightforward, we put our answer down and that's it. We don't have to worry about carrying over anything. But when we have a number where the sum of a column exceeds the base number, in other words, we do not have a representative symbol to place in this column, what we then do is we push across a group of 10 or a group of that base into the next column. So let's have a look at this one then. 9 plus 5 is 14. 14, there's no equivalent to represent the 14 in this column. So what we do is we leave behind the 4 and we carry across a group of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we have 14. We left behind a group of 4, 1, 2, 3, 4, and we pushed across the group of 10. However, we don't need to write 10 here, we simply wrote 1, because 1 in the second column is represented by a 10, a group of 10. Same idea again, we do the same here. 9 plus 1 is 10, plus 8 is 18. Leave the 8, carry the 1. 7 plus 1 is 8, 8 plus 4 is 12. Leave the 2, carry the 1. Add the last column up to give us the final answer of 4284. Let's look at hex now, base 16. Straightforward one, no carrying this time. A is 10. 10 plus 1 is 11. 11 is a B. 7 plus 3 is 10. 10 is an A. 6 plus 6 is 12. 12 is a C. C plus 2. C is 12. 12 plus 2 is 14. 14 is an E. So our final answer then is E, C, A, B. Nothing to carry across, straightforward. Now let's see one where we have to carry things across. 9 plus 9 is 18. 18 is not represented in hex. Therefore, we subtract 16, leave 2, carry across one group of 16 onto the next column. And the same again. 9 plus 1 plus C adds up to give us 22. We subtract 16, move that 16 across as a 1 to the next column, leave behind what's left over. 16 plus 6 is 22. We leave behind the 6 and carry the 1 across and do the same again. So these two hex numbers added together give us EA62. Here's one for you to try. Pause the video, go away, try this. Welcome back. What you should have is D13. 16 plus 3, 16 and a 1. Move the 16 across, leave the 1 behind. 13 is represented by a D. Subtraction. That was addition. Let's look at subtraction in base 10 first of all. Subtraction in base 10. 5 take away 4 is 1, straightforward. 7 take away 4. When the number on the top, when the number at the top is larger than the number at the bottom, it's a straightforward takeaway. We don't need to borrow anything. It only gets complicated when the number at the top is smaller than the number at the bottom. Here we have a 5 take away 9. We can't do a 5 take away 9, so we borrow from the neighbour, reducing the neighbour's value by 1, so that becomes a 6. And we move across a group of 10. 10 plus 5 becomes 15. We can now easily subtract 9 from 15 to give us 6. We have 6 here. 6 take away 8 we can't do. Let me just clear this and just use the slide. 6 take away 8 we can't do. We need to borrow. Reduce the neighbours by 1. Borrow across a group of 10. Group of 10 is added to 6 to give us 16. 16 take away 8 leaves us with 8. And keep going until you have done everything. That's base 10 subtraction. Base 10 subtraction. So what we're doing is we're borrowing groups of 10 from the left hand side neighbour. Borrow groups of 10 because we're working in base 10 from the neighbour. Those come across as 10 units which can be used when we borrow them, making the subtraction easy, straightforward. Now let's look at hex subtraction. This time we're working in base 16, remember, so we have to borrow in groups of 16. A, take away F. A is 10. 10 take away F. F is 15. 10 take away 15. We can't do. We've got to borrow. Borrow from the neighbour. Reduce neighbour by 1. Move across a 16. 16 plus A is 26. 10 plus 16. Subtract 15 to give us 11, which is a B. 7 take away 1 is 6. 6 take away 2 is 4. Nothing to borrow here. 3 take away C, we have to borrow. Borrow from the neighbour. Reduce neighbour by 1. Bring across a 16. Combine that 16 with the amount that you've got in that column and perform the subtraction. We end up with our answer. And you try this. Pause the video. Welcome back. This is what you should have had. 4697. Okay, we're going to move on to binary addition subtraction now. Binary addition and subtraction. Now we know that the computers store everything using ones and zeros, so we are going to use the equivalent kind of system which we've just looked at using ones and zeros. We need to have this table remembered. You need to memorize this table. I'm also going to draw up a table for you just to show you what these kind of look like. So 0 plus 0 is 0, 0 plus 1 is a 1, 1 plus 1 is 2. How do you represent 2 in binary? Well, we've got the columns, of course. Let's draw our columns, 1 and 2. These are the first two columns in binary. There's a 1 here and there's a 2 here. So this is 2 to the power of 0, 2 to the power of 1. We don't need the other ones. So there's 4 here and 8 and 6. We don't need those ones. So 0 plus 0 is just a 0. 0 plus 1 is a 1. 1 plus 1 is a 2. We can't. How do we show a 2 using binary? Well, to show a 2 using binary, it's 0 carry 1. 0 carry 1. The 1 goes into the next column. And that's, of course, 2. This binary number is 2. What about 3? 1 plus 1 plus 1 is 3. How do you represent a 3 in binary? Well, we place a 1 here and we place a 1 here, so it's a 1 carry 1. 1 carry 1. Remember this table, folks, because this is important. This is one that we need to remember. I will draw this table here so that we can refer to it as we're doing our addition, subtraction, or additions rather. So 1 and 2. Yeah. So to represent 1, straightforward. To represent 0, it's straightforward. It's just 0 and 0. To represent 1, to represent 1 plus 1, 1 plus 1 makes up 2. So if you add 1 and 1, it makes up 2 in base 10. How do you represent 2 in base 10? It's a 0 carry 1. How do you represent 3 in base 10? It's 1 carry 1. Okay, let's add these numbers. These are two binary numbers and we're going to do the addition of these two binary numbers. It's a straightforward one. There's nothing to carry. 0 plus 1. I'm just going to continuously add this. It's just so you're starting on the right hand side. Start here, then here, and so on, and just add the numbers as you're going along. That's the addition of this binary number. Easy, straightforward. All you've got to do is add the ones and zeros. That's it. Okay, this one's a wee bit harder. This one is going to have some carries. Let's do some carrying. Let's carry on. That was a joke. 0 plus 1. 0 plus 1 is 1. 1 plus 1 is 2. 2 is 0 carry 1. 0 carry 1. Oh. 0 carry 1. 0 and the 1. Look. Make sure you pay attention to this one. It's 0 carry 1. 1 plus 1 is 2, which is 0, 1. 0, 1 represents 2. That's how you represent 2 in binary. So it's 0 carry 1. 0 carry 1. Then you have 1 plus 0 is just 1. And I'm going to continue this now. 0 plus 1 is 1. 1 plus 1 is 2, which is 0 carry 1. Now, here we go. 1 plus 1 is 3. How do you represent a 3? 3 is a 1 carry 1. 3 is a 1 carry 1. 1 plus 1 is 2, which is 0 carry 1. 1 plus 1 is 2, which is 1, which is 2, which is a 0 carry 1. 1 plus 1 is a 2, which is a 0, carry 1, and a 1. Yep. If you didn't understand that, jump back and watch again. Okay, that's it here. Again, if you didn't catch that, pause and watch. Try on paper, make sure you understand how this works. Here's one for you to try. Pause the video. Welcome back. The answer is this last number. When you add this up, there's an additional 1 at the end. The whole answer, the full answer would have been with the 1 at the end. Now if you only had 10 digits set aside to store the value, you couldn't store that additional bit. This would have resulted in an overflow. We're trying to fit too large a number into too small a space. That's an overflow, and you'll see this as you're coding in programming. When you start to write some code and your calculations exceed the storage space for that data type, then you will see an overflow error. Okay. Subtraction. Let's look at subtraction. 1 take away, this is straightforward. We're just subtracting zeros or ones from 1. Okay, so straightforward. 1 take away 1 is 0. 1. 1 take away 0 is 1. 0 take away 0 is 0. It's a straightforward one. It's just working with number ones. Anyone in primary 1 and below possibly could easily do a straightforward binary subtraction. But when we come across something which is a bit more complex, we have to borrow. Now remember, in base 10 we borrowed groups or chunks of 10. In base 16 we borrowed groups of 16. In base 2 we are borrowing groups of 2. 1 take away 1 is 0. 0 take away 1 we cannot do. We borrow from the neighbour. Neighbour becomes 0. A group of 2 moves across, and then we can do a 2 take away 1 to give us 1. And so on. We keep going, borrowing 2's each time whenever we can't do something to give us our final answer. Here's one for you to try. Pause the video. Welcome back. You should have make sure you understand this. There is another method. The other method is the 2's complement method. You can use either method. Sometimes you could be asked a question to explain the 2's complement method, or what is the 2's complement method. The computer has gates within it. When we go on to look at hardware and how the hardware components are made up inside the CPU, you'll see that the computer can easily manipulate bits and invert those bits, and also perform additions fairly straightforward for a computer to do. So the first step for using the 2's complement method to add or subtract, to use addition to subtract. So 2's complement allows the computer, 2's complement allows the computer to use addition to perform a subtraction. It's like if you think of base 10 and you're adding you add a negative number. So 10 plus negative 5, 10 plus, so you add 10 plus the negative 5 is 5, which is the same as doing a 10 take away 5. It's a similar kind of idea. So first you invert the number that you want to subtract, and then you add 1, and then you add that to the final number. Let's look at an example. So here's one. Top number, take away the second number. So this, take away this. That's what you should get. Using 2's complement, what we do is we take the invert, we invert the number which we want to subtract. That becomes this. Look at the bits. Just look at the bits. We invert the bits. In other words, the 1's become a 0 and the 0's become a 1. So here, this 0 has become a 1. That 0 has become a 1. That 1 has become a 0. This 0 has become a 1, and so on. So you invert the bits. So the first step is to invert. Once we have inverted, we add 1. As in, we add 1 at the end. So plus 1. We perform the addition. 0 plus 1 is 1, 1 carry 1, and so on. So you do all the usual method of adding a 1. And once you've added that 1, you end up with another number. And then with this number, we add this to the number which originally was the number where we were going to subtract from. That's this number. Okay, so that's the same number. This is the inverted and plus 1 number. Inverted and plus 1 number. We now add these two numbers as if we were doing a normal binary addition, which and again we should end up with the same number. These both are the same. Yeah, that's the 2's complement method. This is known as the 2's complement method. So just to summarize then, when we work in hex, we use the digits 0 to F. When we work in binary, we use digits 0 to 0 and 1. Hex addition, when it becomes 16 or more, 1 has to be carried to the column on the left. When we do addition, hex additions, and 16 or more, you have to carry that 1 across to the column on the left. Binary addition, you carry 1 across. Hex subtraction, when you can't do hex subtraction, we borrow 16 from the neighbour. When binary subtraction can't be done, we borrow 2 from the neighbour. And 2's complement can be used as an alternative to subtract binary. That's us, folks. Thank you.